In nature, diets are deeply interconnected. An ecosystem is a massive web linking animals to their food sources. A rabbit eats grass, a horse eats grass, but a cow eats grass and grain. It quickly becomes a tangled, unpredictable network. In mathematics, any loose connection like this between two groups of data is called a relation. We map an input to an output. The danger with a standard relation is ambiguity. Take a student named Rania. If you ask a dataset to identify her favorite subject, it might spit out science, math, and English all at once. One input triggers multiple possible outputs. If you are calculating the load limit of a suspension bridge or timing an investment in the stock market, you cannot tolerate 3 different answers. You need exact figures to proceed safely. Everyday life handles loose associations well, but applied mathematics and engineering require strict precision. Ambiguity makes prediction impossible. 17th century mathematicians like Gottfried Leibniz and Leonhard Euler needed a more rigorous system. They sought a mathematical rule that eliminated guesswork entirely. Their solution was a specific type of relationship called a function. A function operates as a strict machine. For every specific input you feed into it, it is forced to return exactly one specific output. A function strips away the chaos of multiple possibilities to guarantee absolute predictability. To see how this filter operates, we divide our data into 2 distinct groups. The inputs are housed in the domain, and the outputs sit in the codomain. The absolute rule of a function is that every object in the domain must map to only one specific image in the codomain. If one input leads directly to one unique output, that is a 1-to-1 mapping. It passes the test perfectly. A many-to-one mapping also works. If 3 different people buy tickets to a theme park and all pay the exact same flat rate, the output is certain. You know exactly what each person paid. If one single domain input shoots out multiple arrows to different outputs, the certainty collapses. That one-to-many relation fails the test. A many-to-many relation creates similar chaos. When multiple inputs trigger an overlapping mess of outputs, the math becomes useless. By restricting mathematical operations strictly to one-to-one or many-to-one relations, we ensure that every time we calculate an equation, we get a single definitive answer. Once a relationship survives the function filter, we can stop looking at abstract arrows and start visualizing its actual shape. First, we convert the connections between the domain and codomain into ordered pairs, bracketed coordinates representing the x and y values. We organize those pairs into a clean table of values, stacking the inputs neatly next to their guaranteed outputs. That entire table is then compressed into a single equation, commonly denoted as y equals f of x. Finally, we plot those ordered pairs onto a Cartesian plane. By connecting the dots along the x and y axes, the true geometric shape of the function appears. Linear functions form predictable straight lines. Quadratic functions bend into U-shaped curves called parabolas. Cubic functions stretch out into sweeping S-curves. Reciprocal functions fracture cleanly into mirrored arcs known as hyperbolas. These geometric shapes act as a visual vocabulary. They allow us to look at a complex dataset and instantly recognize the underlying pattern. How does recognizing a shape on a graph help us understand physical reality? Consider Malaysian footballer Mod Faiz Subri. In 2016, he won the FIFA Puskas Award for a free kick that appeared to defy physics. This graph tracks the ball's trajectory, which follows a precise quadratic function. The height of the ball over time maps exactly to the equation s equals 25t minus 2.5t squared. Because we mapped that function onto a graph, it forms a parabola. By locating the peak of that curve, we reveal the maximum height the ball reached without doing any complex algebra. Tracing that same curve down to where it intercepts the bottom axis predicts the exact second the ball hits the ground. Graphing the function takes invisible physical forces and makes them entirely readable. This predictive power scales from elite sports down to everyday economics. Imagine an entrepreneur named Anise running a nasi goreng stall. This chart shows her sales volume compared to her profit, which maps perfectly as a linear graph pointing upward. If Anise sets a specific business goal to make exactly 20 ringgit, the graph provides the roadmap. We trace a line from 20 on the profit axis directly over to the linear function. Dropping straight down from exact intersection point to the sales axis gives her the absolute target. She has to sell exactly 40 units. Functions serve a highly practical purpose. They act as strict mathematical filters, allowing us to organize the chaos of reality, extract the underlying patterns, and map out outcomes with absolute certainty.